Next case is the bushing optimization. There is a high voltage conductor passing through the grounded metal wall, and it is insulated by the cylindrical bushing. The high voltage conductor potential is 10 kilovolts. The ceramic permittivity is 2.4. The air permittivity is 1. And our task is to calculate the electric field stress distribution in the insulation and decide if the design is good or not, and offer some ways to optimize the design of the bushing. I create a new problem, specify the location folder and the problem file name. The problem type is electrostatics, the length units are millimeters, and the model class again is axisymmetric. Here I should draw the geometry model. Okay, this is 10 by 5. The horizontal axis is the axis of rotation, so indeed this is, if you rotate this rectangle around the horizontal axis, you will get the cylinder. Now through this bushing passes the high voltage conductor, like this. And this bushing is inserted in the metal wall. And outside is the air. So this is the geometry model setup. Again, here I should assign physical properties to each object. This will be the wall of the tank. This will be the ceramic. This is the air. Well, in transformer it could be oil, but in our case inside the tank is air. So again air. And this is the high voltage conductor. Well, the wall has 0 electric potential, so for the wall surface I assign the label grounded. And the conductor has high voltage potential. For the conductor surface I assign label HV. So this is all. Now we should assign physical properties to each object. For the air I specify the electric permittivity of the air 1. For the ceramic I specify the electric permittivity of the bushing ceramic 2.4. For the conductor I do not specify any properties, there is no electric field inside the conductor. Instead, for the conductor surface I specify the high voltage potential 10 kilovolts. For the wall I do not specify any properties for the wall block because there is no electric field inside the metals. Instead I specify the electric potential on the wall surface. The wall is grounded, so the electric potential is 0. Now we can build the finite element mesh, save all problem files and run the analysis. here you can see the field lines, and again I will adjust the field picture and switch on the color map of the electric field strength. Well, as you see, the electric field stress here is higher than the allowable stress for the air. It is 5 kilovolts per millimeter, and the allowable stress is only 3 kilovolts per millimeter. So indeed we would like to reduce the electric field strength. How it could be done? Let's imagine that we wrap the bushing with some aluminum foil. So there will be some foil here, which will redistribute the electric potential and accept the electric potential of the grounded wall. Now let's simulate this case. This edge is the aluminum foil, and it will have the potential of the wall, the grounded potential. Now let's again simulate this case. Now let's take a look at the electric field stress distribution. You see, we eliminated points of high electric field strength, but I will select the surface, this surface, and take a look at the electric field stress distribution along this surface. That point here, and you see the electric field stress here is higher than the acceptable 3 kilovolts per millimeter. Again, we need to optimize the design of the bushing, and now I will change the form of the bushing. It will be the cylinder, but the cylinder of this form. Let's again run the simulation. And again I will switch on the color map of electric field strength. Now this high peak value corresponds to this point, and this value, which is also high, corresponds to this point.